convolutional neural network. And this is kind of the go-to model for anything image related, right? Okay, so let's get started. Okay, so up until now, you should recognize this as just your traditional neural network. And, I just have a sample problem up where we might have a neural network that predicts the number of schools given some information about the neighborhood, right? So if you remember, these guys are called features, right? So if you have 10 features, then our model has 10 input neurons. We then throw that through the hidden layers of our model. All the orange guys are neurons, right? With your weights, biases, activations. And finally, at our output layer, we get our single output, which is number of schools. So we're predicting a continuous number here. Does anyone remember if this is classification or regression? Just a quick review. Regression, yeah, because we're predicting a continuous number. If we were predicting like type of school or something, like 5 types of schools, then that'd be classification. Okay. So question, let's say we wanted to work with images. So let's say try to classify this image as what type of number it is. How would we input that into a neural network? How would we, right? Any ideas? The pixel values? Yeah. The pixel values you said. Yeah. What was your name? Shoots. Shoots brings up a good point. We could maybe like unravel the entire neural network and just, if this is like a 1024 by 1024 image, we could have that many neurons in our input layer. And yeah, that is one possibility. But is there a better way? So CNNs provide us a much, let us accomplish the same goal of taking images as inputs without having a massive input layer. And if you may remember, we want to avoid like unnecessarily large neural networks because they lead to overfitting, right? So here's the rough architecture of CNN. As we proceed, we'll be discussing what each layer of this thing does. Okay, so first, let's talk a little bit about images. So for the first part of this lecture, we'll be discussing black and white images. And so here, the dimensions of our input would be height and width, right? So height, width, and picture this as like a 2D array, right? Where every element is your pixel value. So, for example, pure black pixels would be 0. Pure white pixels would be 255. Anything between would be a number between 0 and 255. Okay. So one of the biggest operations in a convolutional neural network is the convolution. And so there are kind of 2 parts to this operation. One is the kernel. The other part is a subset of your image. So you take some n by n matrix called the kernel. So this is 3 by 3 in this case. And you identify a n by n portion of your image. So in this case, I've isolated the top 3 by 3 portion of our number 5 picture we had earlier. And you do element-wise multiplication between the kernel and the image window, right? So what that means is we take this -1 on the top left corner and we multiply by the top left corner of our image window. And then we take the second element, we multiply that by the second element of the image window. And we just go back and forth, back and forth. So we then take our final output and sum them up to a single value. In this case, 146. Let's go through a more like concrete example. So you can see that in our element-wise multiplication, we do -1 times 0, -1 times 30, -1 times 36. And we have all these calculations reflected here on the right-hand side, and we just sum them up to 146. Okay, so you can, this may be a kind of a leap in understanding, but you can almost imagine this kernel as extracting the important stuff within our image, within this single section, right? Kind of akin to how weights,
So when it says like outputs do not have to be between 0 and 255, like what is like a situation where you would not have them be between 0 and 255?
Imagine your kernel numbers are all like somewhat big.
Oh, so that means like the output have to multiply everything. Okay.
Yeah,
gotcha.
and then you sum them up. Yeah. So what we then do is we take this window and then we start by multiplying on the top left corner and then we move that 1 over. And so we do this operation for every single one. So over here, for example, so up until now, everything's zeros, right? So our element-wise multiplication and summing would yield us 0. here we start to see like a 30 on the bottom right corner. So our output is -1 times 30. We get -30 as output. So we keep sliding this window over and just record that output number every single time. And so the amount we slide our window by is called the stride. So in this case, we're shifting our window to the left by 1. And then once we're done with a single row, we shift it downwards by 1. So that means we'd have a stride by like 1 by 1. Okay. So how do we pick our kernels? Well, just like similar to weights in a traditional neural network, our kernels are learned, right? And the idea of a kernel is that we want to learn this feature map somehow. So the output of all of our multiplications between our kernel and images, you could almost visualize them in this feature map. Now, remember, feature maps, like the outputs, aren't necessarily 0 by 255. So this is just like a simplified image here. So for example, this white square might be like 1,000. I just, visualize it in a nicer way. Right. So again, this feature map is the output of our convolutional step. They're just illustrating that. And so, all right, and I'll explain what a feature map is in just a second. But okay, so again, stride is how much we move our kernel by. So it's 2D. So the first dimension x is how much we move over it to the right. The second dimension 2 is how much we move it downwards. Everyone clear on what stride is? Okay, perfect. Okay, padding is to artificially make our output a little bit bigger. So in this case down here, we've padded our image by adding this perimeter of black pixels, right? And this just increases the size of our image. Right now, just think of it as an operation. We'll discuss why it might be useful in a little bit. Okay, so back to the feature map, right? The output of our convolution operation. So different feature maps represent different things being made. So remember, these kernels are almost like weights in our neural network. They extract important information from our original image over here. And so if we have 2 different kernels, we're learning 2 different feature maps, which means 2 different representations of the image that the model better understands. So naturally, if you wanted to do if you want to give the model as much room as it wants to learn as many different feature representations, you could do 64 different convolutions all at once, right? So that means you'd have 64 different feature maps. And again, each feature map is a different way for the model to interpret the image. So just looking at this, that just looks like a fat 5. It looks like a fatter 5 to us, right? But the assumption is that the model is better able to understand what this is compared to what this is, right? Okay. And again, that is 64 different operations in parallel. So from a performance perspective, having more convolutions obviously gives your model more space to learn. But at the same time, it does make a large model more prone to overfitting, more computation. So it is a little bit of a balancing game. Okay. So let's talk a little bit about our dimensions. Remember, we started by a 2D input, right? Height by width, right? After we say do 64 convolutions, our dimensions are no longer the same. So let's say we have a stride of 1 by 1, a padding of 0, and a kernel size of 3 by 3. Do you guys think the outputs feature map for any convolution is the same dimension as the input? So in other words, is doing a convolution mess with the input size? Does it make it smaller? Does it make it bigger? What do you guys think? Or does it stay the same? Any takers? Gets smaller. All right. That is correct. So generally, just doing convolutions makes your image smaller. So here's a rough formula to kind of show what's going on. So generally, a bigger stride means a smaller image. And so if you remember that sliding window, that means you're taking bigger jumps. So you're skipping more of the image. So your output, of course, is smaller. If you have a bigger filter size and kernel oftentimes used interchangeably. So if you have a bigger kernel, of course, a smaller image. So here is where padding is useful, right? Let's say you don't want your image to shrink after every convolution. You could pad your input image, right? So your output stays the same size. So again, you can see that filter size and stride decrease the image size, padding increases it. So if you don't want your image to shrink too quickly, you would pad it by adding like zeros on the edge of the image. Okay, so that is it for convolutions. Any questions about how those work?
All kernels have to be the same size? Can you vary it?
Traditionally, yes, if they're on the same layer. Now, you might see here that I've stacked, I'll get into this a little bit, but I have different convolutional layers. So these kernels might be 3 by 3, these might be 5 by 5, right? But generally on the same layer, if you have like 64 kernels on the same layer, they'll all probably be the same size. Okay. All right. Okay. Now after you do, let's say this is a excerpt from our feature map. Remember, that's the output of doing our convolutions. We would then apply a activation to it, similar to, after your weights and biases in a traditional neural network. And again, remember, kernels are learned, right? And they're trying to learn like nonlinear representations, again, similar to a neural network. So having an activation layer in the middle helps us do that. Okay. So as I was saying earlier, we oftentimes stack convolutions like in sequence. So again, like we may have a convolutional layer here, and then the activation, and then we stack another one, right? And in doing this, we could learn more complex features. So for example, maybe the first convolution can see how pixels adjacent to each other interacts, right? And the next convolution can see how the features interact at a like larger scale, right? So by stacking convolutions, we can learn, there's way more space to learn more complex features. You could almost think of it as adding more layers in our neural network, right? Okay. And remember, if you kind of look at the image a little closely, you'll notice that this second convolution has slightly more padding than this first convolution, right? So we oftentimes don't want our images to shrink too quickly. So padding is a great tool for that. Okay. So, right. So as I was alluding to a little bit earlier, if we do something like a traditional like 3 by 3 kernel, like something like small like this, we only see how like pixels are like closely related interact with each other. How do we learn how pixels are farther apart interact with each other? For example, let's say I want to understand what a 5 looks like. I could try having this massive kernel to learn like large features like this. So we could just have massive kernels, or a easier way to do this is to do something called max pooling, which is a lot less computationally expensive. Okay, so in max pooling, we take like some n by n window, right? Again, this would be in our feature map, so the output of our convolutions. And then we just simply pick the biggest number in that window, right? So for example, in this window, 648 would be the biggest, and we would just extract that, and that would be our output from this max pooling. So for example, if we were to do max pooling like across our image, so in this top right corner, it would be 0. And then notice, instead of sliding the window by 1, we just make a full jump, right? So our stride is significantly bigger. So in this case, the stride is as big as the pool size in max pooling. So we keep just finding the maximum values from these large portions of the image. So in this case, 213. So why do we do this? Oh, by the way, yeah, we also truncate. So you see the sliver doesn't properly line up. We just skip that. We just ignore it. The assumption is that this is padding or something like that. Okay. So why do we do this? Again, it's a great max pooling kind of summarizes the feature map. So again, the reason we're doing this whole CNN thing in the first place is that we don't want to be working with a massive neural network, right? So convolutions, you can think of them as extracting useful stuff from an image. Max pooling is kind of summarizing that feature map, right? So we're just extracting the biggest number in this window size of ours. So if this is like 1024 by 1024, this is like maybe half that size or a third of that size. Okay. Right. So this is just talking about stride. Right. So before I show the formula for comparing the dimensions of the input and output for convolutions, here's like the dimensions for like after doing max pooling. Right. So we start by 20 by 28 image. If we do a max pooling with a window size of 3 by 3, we end up with a 9 by 9 image, so significantly smaller. Okay. All right. So we're almost done with our convolutional neural network. We've done convolutions to extract the interesting stuff in our image, max pooling to kind of summarize that feature map. Now we're back to a neural network, right? And so we're familiar what this looks like. Every neuron is an activation, just weights times the input plus bias, and then does an activation over that. Okay, we're very familiar with this, but we're almost back to the same problem, right? So now we have this we have all of these different feature maps. So again, if you had 64 kernels, we'd have 64 feature maps, each one representing a different view, like a different representation of the image. But again, we're back to the same problem of how do we input this into a neural network, right? Because, okay, sure, like these feature maps are useful like to the model, maybe they contain some great information, but we want that output. Like we want to classify this as like, what number is it, right? Okay, so the operation that permits us to do this is called flattening, or just flatten. And the idea is, as Shub was alluding to earlier, we just unravel the image like at the pixel level. So we start up, kind of imagine like an S, like a snake winding up. So these top left pixels will be mapped to like up here, and then we just continue unraveling kind of this S-like shape. And then, so we go from like a 2D mapping. So let's say this is height by width to a 1D mapping of 1 times height times width, right? So now that we flattened this, right? Each of our now, I hesitate to say pixels, because remember our feature maps are not actually pixels, but we now have these like values from our feature map that we could just plug into our neural network. Yeah. Yeah. So the goal is to map this 2D image to a 1D like array, right? And so we begin on the top left corner, and then we take this element, and we put that as like the top of our 1D element, right? And then we take the second element, and then we put that on the second element, right? So the first, let's say, K elements in this 1D array come from this first row. Does that make sense? And then the next K elements on this 1D array come from the second row, right? So yeah, imagine like maybe geometrically, if you could like envision this, take this row and then just flip that over 90 degrees and put that here. And take this row, flip that over 90 degrees and put that here. The point is we just want a flat representation of our feature map. Okay. Right. So you might remember though that we have like not just one feature map, we might have a bunch of feature maps, right? And so we would just flatten each feature map and then stack them one on top of the other. Great. So yeah, we've now almost completely gone over how to create a CNN, right? Convolutions, max pooling, and then we have our neural network, which in this case just we call a dense layer. So imagine like the hidden layers of a neural network. Okay. So just some review over traditional classification.
So for like the input into the dense layer,
Mhm.
are you inputting like separately the like the max pool unraveled and then also like the convolution unraveled?
So the input to the max pool step is the convolution.
So then you only have the max pool.
Exactly.
Okay, got it.
And then you flatten the max pool, and that's your input to the
Okay.
network. Okay. Right. Yeah. Any questions? Right, perfect. Okay, so this is just review from traditional classification. Does anyone want a review of like softmax and how that stuff works? All right, let's go for it. So, okay, so in our example, right, we want to classify, let's say we have 6 numbers in our database, in our data set, right? 5 is one of them. And so for every classification, for every class, sorry, that we want to classify, we have that many output neurons. So in this case, if we have 6 numbers, we have 6 output neurons, right? So each output neuron produces a score called a logit. And so the higher the score, the more likely it is that class. So for example, 5.1 is like the logit for the second neuron. That means like, let's say the second neuron is trying to predict measures if it's the number 2 or not, right? That means, okay, 5.1 is a high score, it's probably that neuron, right? But traditionally, we don't just stop here. We do something called a softmax. So what that does is that it maps all of these numbers that are they're literally any like continuous number, negative, positive, anything. And it maps these numbers to a probability. So now notice that 5.1, that's been mapped to 0.9. So if you sum all of these outputs, they sum to 1, just like a probability. And we have no negative numbers, right? And so this is just a rough form to do that. I know it looks kind of weird, but what we're essentially doing is that for each output logit, we take e to that number. So for example, for this first one, we would do e to 1.3, and then divide that over the sum of all of the other logits minus the e, right? So it's kind of like a percentage, right? But yeah. And then we would just pick the highest probability. So again, that'd be 0.9, which is from the 5.1 logit. No, they don't. Good question. That's why the e raised to the logit is really small. Like if you do e to the negative number, that would just be a really small number. It's a really small positive number. Ion.
Why do you need to do softmax if you can just pick the biggest number?
Great question. Back propagation. If you remember, like back propagation involves us doing going from our loss function and then moving backwards and like taking derivatives and stuff, right? So you can take the derivative of softmax, but how would you take the derivative of just picking the max value? So yeah, does that answer the question, Ryan?
Do we have to do like, is softmax necessary, or can we use like other activation functions as long as they're like stand up 0? Like the like RayLoop, what we did for the pooling there.
So let's consider doing that. Let's say we were to apply RayLoop on this output layer. All we would do is just snuff out any 0 number, right?
Yeah.
So in this case, we wouldn't really have an effect. And then you're proposing, so we do RayLoop on this, and then we just pick the max number after that. So that is viable, but softmax is better for 2 reasons. One, having this probability, like in this probability form, like to us is a lot more interpretable, right? Like it's kind of a percentage, like confidence in that class, right? But more importantly, it shrinks these logits that could be like minus 1,000 to positive 10,000 to be between 0 and 1, right? Not only that, it exaggerates the differences. So for example, proportionally 1.3 and 5.1, or maybe like 1.3 is 3 times less than 5.1. But you can see it's been mapped to 0.02, and 5.1, this has been mapped to like 0.9. So proportionally, it really exaggerates the difference, right? And we actually want this behavior because that way our model can more strictly penalize predictions. So for example, if we just ended here, right? Our model might kind of penalize it for predicting 1.3. Sorry, let's say 5.1 is the incorrect number and 3.1 is, sorry, let's say the second output is incorrect and we actually want this first output. So in other words, our model was incorrect, right? It said 5.1, class 2 was the highest, in reality, class 1 was the highest, right? So doing something like a softmax would be way stricter because this would mean, hey, the model's super confident, like 90% confident that class 2, we need to penalize this a lot harsher compared to an output of like 5.1 relative to 1.3. Did that make sense?
So is softmax like the standard for everything after the output layer?
For classification, generally, yes.
The real question, say that your logits were all negative, then you couldn't make a prediction.
That's a big one as well. Okay, so this, I think I've kind of explained this, so we're going to move on. Okay, so here's just the summary of what's going on. So convolutions learn what to pay attention to in an image. So if we have a bunch of convolutions all happening at the same time, that offers that many ways of the model to interpret the image. Max pooling then takes each of those feature representations and it summarizes them just by picking the biggest number. The dense layer is just our traditional neural network, right? It unravels, like it flattens the stuff from a max pooling and it just shoves that into a neural network, what we're familiar with. Finally, just our output layer that gives us our output. Number 5, classification. Okay. So up until now, we've been talking about working in grayscale, but in reality, our images have like, RGB, they have a color in them, right? So how do we do convolutions on images with color? Right? Any guesses? Ayan.
Well, there's 3 channels, right? So just do it like split it into 3 separate images.
Exactly. So we begin by, okay, so we have RGB. Remember, convolutions work on like a 2D image, right? So grayscale is a 2D image, it's very easy to work with. But RGB has 3 channels. We just consider the red portion of that separately, the blue portion of that separately, and the green portion of that separately. But if you're not familiar with RGB, like the first element denotes how red the image is, second element is how blue the image is, or sorry, RGB. Second element is how green the image is, and the last one is how blue the image is. So we just separate the redness, the greenness, and the blueness channels, and then we're ready to do convolutions as normal. So we do, we do a separate convolution on each of these 3, and then we just add them up, right? And we only really have to worry about this for our first input layer, right? Because afterwards, we're just working with feature maps, just like in a standard grayscale image. So in other words, for our very first convolution, if we're working with images, we just have to separate each of the channels, and then afterwards, we're ready to go as normal. Okay. Yeah, that's pretty much it. So let's kind of think about what this might look like in code. So VGGNet was one of the big early CNNs produced by Oxford, and it gives a little bit of insight on how CNNs are like formulated in practice. So the model I've been working with is a little bit of a simplification. Okay, so I've commented a lot of the code out because it's redundant, but it works by having 5 of these almost identical blocks. So I've shown one of these blocks for simplicity. And so I've illustrated what one of these blocks looks like. So we start with a convolution layer, our activation layer, which is ReLU in this case, another convolution, another ReLU, and then another max pooling, right? Again, don't get this confused with the softmax. This activation is like in between convolutions to learn nonlinearity. That softmax that we were just talking about is at the very end, like of our dense layer, right? For our final classification. Okay, the idea is we have like 5 of these almost identical blocks that feed into each other. So the max pooling layer of this first block feeds into the convolution of the next block. Okay. So why have so many of these blocks, right? And that kind of goes to why we stack convolutions in general. By having these blocks, it gives us some room to like, each block can extract different types of feature maps from the image. So this first block, for example, can examine how pixels like that are right next to each other interact. So if we input our image of a cat, we might get this as output. So you can see that like we have the rough, like the edges, the contours of the image like highlighted, right? The next block might recognize at a somewhat higher level. Like for example, it's kind of highlighted like the nose of the cat. You have a little bit more detail on the ears. The final few blocks would highlight like more global features. So for example, you can identify, hey, that's like a roughly an ear shape, that's roughly a head shape, right? So each convolutional block extracts like more global features. Emma.
Is there a reason we're feeding like the product of one convolution to the next? Like, can't you misstep that, or do you just have to order them in there?
So why stack them as opposed to?
So, like when you put the image through that first convolution layer to highlight like that type of contouring, I guess, are you feeding that image into the next convolution layer, or are you
Yes.
feeding something like can't you misstep if like that particular image highlights certain things that like the next? Does that make sense?
Yeah, I get what you're saying. You can almost think of it as like a funnel, right? Of learning more and more useful representations. So in other words, you can maybe you can assume that this representation is better for the model to understand than the original RGB image, right? So this is easier to understand for this block compared to the original image. So this first block is learning, okay, how can I best simplify or represent this image so it can be better fed to the next steps? Does that make sense? It's kind of like a, right.
So if you essentially took out max pooling for that process and, so you're like not shrinking your feature map now? And then that means you're overfitting like constantly or?
Potentially. So max pooling lets us shrink our image, right? So you can notice that the resolution is decreasing as we move down, right? So if we remove the max pooling layer, pretty much each of these intermediate images would be the same size, right? Which means we would have, so you can imagine that the kernels are really big here and the kernels are smaller here because our images are smaller. But, if we kept these the same size, then like, we would have more, we need more kernels. And then finally at our final layer, like our dense net layer, like our neural network at the very end of the process would have to be really big. So yes, in short, yes, we might be more prone to overfitting. Okay. Right. And this is kind of illustrating what I was talking about. So the first convolution, if our kernel is like 3 by 3, that's like super, super tiny, right? So we're really just examining how like pixels that are this close to each other interact. And then on the next convolution, well, a 3 by 3 kernel is like proportionally a lot bigger. So now we can see how like features that were originally farther apart interact now, right? And so we keep going through this process and until we've kind of like really simplified this image to its like bare bones, exactly what we need for our final classification layer. Okay, so in other words, a model, our neural network now just has to be 6 times 6, so 36, input size of 36, as opposed to 2,156, right? And directly feeding in this input, like directly flattening this input in, maybe we have a bunch of information here that the model does not need. So again, those blocks of convolutions are just, how can we only give the model exactly what it needs? Okay, so as for more code related stuff, well, syntax, yay, not my favorite part, but it's still useful to know. So conv2d is like, nn.conv2d is our PyTorch function. That is like just a convolution. So this first number is our channel. And so remember, height, width, channel is like the dimensions of our inputs. So we specify the channel size, and then we specify the output number of channels. So this is also like the number of kernels we have. So if we have 64 kernels, then we'll have 64 channels. Because again, each kernel learns a different feature map, right? And each feature map is another channel. Okay, and we specify kernel size and padding. And we've already seen these things before. We know what ReLU does. Okay, and again, the first number is the input channel size, and then this is the desired number of channels. Sorry, not channels. Input number of channels. This is the output number of channels. And then, yeah, that's pretty much it. Max pooling, we just specify the kernel size and stride. But yeah, that's pretty much it. Okay, so question. This might be a little tough. So we do 5 of these blocks on the original image, like, sequentially, right? And remember, we do max pooling at the end. So every time our image gets like drastically smaller at each output. So can anyone like maybe understand why? So if our original image sizes are 224 by 224 by 3, ignore that. That should be by 3, the channel size, RGB. So if the original image is 224 by 224 by 3, well, why would our input size to our linear layer be like 512 times 7 times 7? Like, any idea where we came up with these numbers? If this is what we started with. Again, ignore that, should be a 3. All right, so this 512 is a little bit misleading. Let's start with how we got with the 7. So we start with 224 by 224 by 3. So again, that's just our image length and height. We have 3 channels for RGB. So at the end of each block, remember, we do a max pooling, right, with a kernel size of 2. So what that effectively does is that it halves our image, right? So at the end of each convolutional block, we're halving our image. The 224 divided by 2 is 112, divided by 2, divided by 2. And at the end, we end with 7 by 7. Right? So this 512 is our number of feature maps, like our number of channels. Right? So 7 by 7 is like the height and width of each of our feature maps. 512 is the number of feature maps we have. So does that make sense? Okay, great. And I was spouting out a lot of numbers. And again, the number of kernels you have is the number of channels you have. In this case, max pooling size of 2 by 2 halves our image in height. Okay, great. The reason I'm kind of harping on this math stuff is when you're designing your CNN, you have to be keeping track of your like dimensions that after each layer, right? Because here, like we just keep track of our kernel size, right? Sorry, our kernel size, our padding, and like the number of channels we have. Like we almost forget like the size of our image after each step, right? So it's important to maybe by hand keep track of how large your image is getting as it passes through these convolution layers. Okay. Aside from that, again, this flatten step takes our 7 by 7 by 512. So that again, that's like in 3D and flattens that to a 1D array with that number of elements. Okay. Okay. Yeah. Okay. That was a lot of stuff. So we'll be spending the last 20-ish minutes, I guess 23 minutes, working on a actual coding example that Vias has been working hard on. So again, this is actually not on the website. I will be putting this on the Discord so you guys can get started if you guys want to. But yeah.